So we're doing a planned comparison off of the ANOVA that we did last time. For planned comparisons, you're really limited to the number of groups that you have, -1, because whenever you have a family of hypotheses, that's called the family of hypotheses, each hypothesis has its own type 1 error, and that's called the per comparison error rate. If you put all of the type 1 errors together, that's called your family-wise error rate. So basically, the whole assumption is that if you have an alpha level of 0.05, that means that 5 times out of 100, we could get significance due to chance alone. That's our type 1 error rate. So if we have a bunch of comparisons that we try to do, chances are we could get significance, even if we don't really have it. So number of planned comparisons that we can do, and by planned I mean you're doing it before you've seen the data, is limited to your number of groups -1. So here it would be 2. Before you have to start correcting for type 1 error. So to do planned comparisons, say for example, we could compare any of these, but we're limited to 2, right? So we could compare A1 to A2, or we could do A1 to A3, or we could do A2 to A3. So just as an example, I'm going to do A1 to A2, and I'm going to do A1 to A3. So for our second comparison, and this is just an example, I'm going to do A1 versus A3, which means I'm trying to see if the significant difference that we got from our overall ANOVA came from the differences between A1 and A3. So I'm leaving out A2. So I'm going to do coefficients of 1, 0, -1. And again, these are arbitrary numbers. You could also do +1/2, 0, -1/2, just as long as these add up to 0. So I'm going to plug the same numbers into my equations up here. So again, that is the sum of all my coefficients times the means of each of my groups. So coefficient for A1 times the mean of A1 is 3.5. And I could leave out group 2 because my coefficient there is 0. And then my coefficient for A3 is -1. Okay, thanks. And my mean for A3 is 6. So when I calculate that out, I'm going to get 2.5 minus?
Yep.
Okay. I'm going to put this number, which is my psi, turn back into here to get my sum squared for this one. So n, again, is the number of subjects per group, which is 4. My psi is minus 2.5, and I'm going to square that. And then this is the sum of all my coefficients squared, right? So I've got 1 squared plus 0 squared plus -1 squared. Since these are also called single degree of freedom comparisons, your degrees of freedom here are always going to be 1. The reason for that is that we're only comparing 2 groups at a time, right? Even if you tried to composite them and said A1 and A2 versus A3, you would still be putting 2 groups compared to each other. If you try to compare more than 2 groups at a time, you would have to use completely different equations. So my degrees of freedom for my single degree of freedom comparisons is always 1. Mean squared, which is our true variance estimate, it's also the error term, is going to be sum squared divided by degrees of freedom. So it's just going to be the same because I'm dividing by 1. To get my F values, it's just going to be my mean squared divided by my mean squared of the within term, right? This is also called my error term. The reason for that is that in ANOVA, we're basically looking to see if there's a difference between 2 groups. So we want all the variance to be between the groups. If we have a lot of variance within one group, it's going to be very difficult to show that 2 groups are different. So the within variance is also called the error, because that's going to be something that's happening that's not attributed to our treatment.
This is also called my error term.
The reason for that is that in ANOVA, we're basically looking to see if there's a difference between two groups. So we want all the variance to be between the groups. If we have a lot of variance within one group, it's going to be very difficult to show that two groups are different. So the within variance is also called the error, because that's going to be something that's happening that's not attributed to our treatment.
So here, my F value is going to be 3.125 divided by 1.08. And here, it's going to be 12.5 divided by 1.08. So these are my F values. Again, if your comparisons are orthogonal, which means that they are independent and non-overlapping, then the sum squared of all of your individual comparisons added should equal your between sum squared. Here, our comparisons are not completely independent and non-overlapping because I used A1 twice. So from these F tables, we're going to do the exact same thing that you do in ANOVA. So you're going to take your degrees of freedom, and we're probably going to do it in a 0.05 alpha level because that's what we like. So degrees of freedom is going to be 1, and your within term, 9. You're going to look that up in the back of the book, and you're going to get a critical value of 5.12. So this is our F critical value. Critical always refers to you get it from a table, and it's 5.12. Now remember, our obtained F values, which is also our F calculated values, always need to exceed this number. An easy way of remembering is that you did all this work to get these numbers, so you just want them to be bigger, whereas this number you're just getting from a table. So since this number is not larger than an F critical, this one is not significant at the 0.05 value. However, 11 is larger than 5, so this one is going to be significant at the 0.05 value. That means, since our comparison 2 was A1 versus A3, that our A1 and A3 groups significantly differ at the 0.05 value, but our A1 and A2 groups do not significantly differ. Okay.
Outstanding! Oh my goodness gracious.